Welcome to this video on capacitors in parallel. Now up to this point we've looked at some of the basic ideas of the difference between a circuit element that's connected in series with another or in parallel with another. Then we came up with some expressions for the capacitors in series, how to find the equivalent capacitance, and now we're looking at the same for parallel. So what I'm going to do here is I'm going to draw in my battery. And I'm going to connect this battery to one capacitor. And then I'm going to do the same and connect it to a second capacitor. And keep in mind here that these little regions are splitters, nodes, or junctions. And what that means is that each capacitor is almost connected or is connected independently to the battery, as would be this one. We're going to label this one C1 and C2 so that we can make some comparisons. Now what's going to happen here is the battery is going to pull charge off of C1, this first plate, and dump that onto the second plate. So let's say it pulls off 4 electrons, like we said before, and those 4 electrons are going to be dumped onto this plate, so I will have 4 electrons showing up here. Now the same thing should happen on this side, right? I'll be able to pull 4 electrons off of this plate, right? So that I'm left with 4 holes, and those same 4 electrons are going to be dumped onto this plate. Now it's really important for us to establish the idea that it's not possible for the electrons to go through this way, right? These 4 electrons over here can't pass through this way because they would be moving against the potential that is established between these two locations. Now let's take a look at what's happening. If we label these points here, I'm going to label these A and B. We'll label these points C and D, and label these points E and F. We know that after a long period of time, the potential difference across A and B is going to be the same as the potential difference across C and D. And we can say then that the potential difference across E and F is going to be the same as the potential difference across C and D. And so basically what's happening here is that the potential difference is the same between all of these corresponding points in the circuit, meaning that the potential, the total amount of potential provided to the circuit, which is the CD, sorry I left out the V here, the CD here is the same independently for both of these. So in other words, the voltage is not shared between the two capacitors. It's independent for each one. So the total is the same in each place. Now if we take a look at the charge, this is a little bit different because the charge that's coming off of this capacitor, this EF capacitor, is a separate amount of charge than is coming off the AB capacitor because these two are independently connected to the battery. Remember, the electrons that we pulled off of E went through here and got dumped onto F, and the electrons that we pulled off of A went through here and got dumped onto B. So in other words, the charge on capacitor 1 and the charge on capacitor 2 added together would give us the total amount of charge in the circuit, or the total amount of charge between the capacitors. Now again, we're going to use our expression that we've come up with before, which is C is equal to Q over delta V. And what I'm going to do here is solve for Q, and the Q would be equal to C delta V. Now the reason I'm going to do this is I want to substitute in an expression for Q here so that I can make capacitance part of this expression. So what that means is I get C1 times delta V over capacitor 1, which we said was delta V AB, plus C2 times the voltage across EF. Now you could have just put 2 here and 1 here. That's just fine. And then over here, we're going to put the total equivalent capacitance, right? That's the capacitance that these two are equivalent to, times the voltage across CD, which is the battery. Now we see here that all of these are the same. So effectively what I can do is I can factor out the potential difference from every term because it's the same. And what I'm left with is that the equivalent capacitance of this configuration is the capacitance at 1 plus the capacitance at 2, which gives me the expression for finding the equivalent capacitance of capacitors that are attached in parallel to one another. If I was to add a third branch here with a third capacitor, I would just have to add this on to the end. Now we can see that for parallel, the reason that this is true is because the charge is not the same charge that's shared between the two plates. It's independent. But when we connected capacitors in series with one another, what we found was that the capacitance was equal to 1 over the capacitance at each capacitor, all to the negative 1. So this was for series, finding the equivalent capacitance, and this was for parallel. In subsequent videos, we're going to start taking a look at resistor capacitor circuits, RC circuits, and a lot of these rules that we're discussing now will come into play in other useful forms.